Welcome back. I'm Sherry Sue, and you can find the full research for today's episode over at sherrysue.com. Right now, the buildings we live and work in are responsible for roughly 40% of total global energy consumption. We assume green architecture has a universal look. We picture solar panels, smart glass, and heavy insulation dropped seamlessly into any city on Earth. But data from thousands of certified projects reveals a massive flaw in that logic. A design built to perfectly conserve energy in New York might actually bleed power if you drop it into Dubai or Singapore. The path to net zero cannot be solved with a single copy-paste blueprint. Instead, global building efficiency is dictated by a complex equation of 3 hidden variables. This map shows the Köppen-Geiger climate system, dividing global building data across 4 major populated zones. You might expect extreme environments to drain the most power. But the data shows that temperate zones, areas with mild, distinct seasons, are actually the least energy-efficient environments globally. Buildings in these regions carry a double penalty. They expend massive amounts of energy battling both heavy winter heating loads and intense summer cooling loads. Take heavily insulated walls, a standard passive design strategy. It works perfectly to trap warmth inside during December. But come July, that exact same insulation traps unwanted solar radiation, turning the house into an oven and forcing the air conditioning into overdrive. Passive design fails unless it is hyper-localized to the specific weather right outside the window. Generic best practices are essentially useless here. That brings us to the second variable, building type. Across the board, residential homes set a strong baseline, ranking as the most efficient buildings globally. Industrial buildings, however, are wildly unpredictable. Their efficiency relies entirely on geographic context. In tropical developing nations, industrial structures are often highly efficient because they utilize brand new manufacturing technology. Contrast that with dry climates like the Middle East, where older infrastructure and petroleum industries drag efficiency to the bottom of the scale. You cannot judge a building's potential for net zero without understanding the specific industrial and geographic context it operates within. The final variable is regional economic wealth, measured by purchasing power parity and gross national income. We naturally assume that wealthier regions have the capital to build the greenest structures. This animated scatterplot charts economic wealth on the horizontal axis against building energy efficiency on the vertical axis. The data shows a strict negative correlation. Higher economic wealth actually correlates with lower overall building energy efficiency. The mechanics driving this are behavioral. As incomes rise, populations demand larger homes, install more energy-hungry appliances, and require continuous, lavish thermal comfort. This behavior amplifies severely in regions with cheap, highly subsidized energy. In the Middle East and North Africa, high wealth and low energy costs combine to drive massive consumption and waste. Capital alone cannot buy sustainability. Without conscious constraint, wealth merely buys a greater capacity for energy consumption. Because climate, building type, and wealth interact so unpredictably, a successful net zero strategy demands absolute hyper-local context. This map shows the fragmented global implementation of building energy codes. Localized codes are our primary tool to force compliance. They must account for urban form. Data proves high population density in compact cities minimizes exposed surface area, reducing the energy required for climate control. Compared to sprawling suburbs, building up into dense, vertical urban centers is inherently more efficient. True sustainability isn't achieved by slapping a generic green label on a project. It requires engineering specifically for the climate, economy, and city you actually live in. For the full scientific breakdown of this data, visit sherrysue.com.